It's a crisp afternoon over the Eastern Shore today as the countdown continues to our latest mission from Rocket Lab Launch Complex 2. You can see our Haste suborbital rocket right there on your screen, getting ready for liftoff from the Mid-Atlantic Regional Spaceport on Wallops Island, Virginia. Now, just minutes away from launching our next hypersonic test mission for the Department of War's Defense Innovation Unit. My name's Hannah Jury, and it's great to be here with you for this exciting experimental mission.
And my name is Muriel Baker, and we are just 21 minutes away from our target launch time today of 4:50 p.m. Eastern Time. And things are looking good for an on-time liftoff today. The weather outlook is 90% favourable for launch, and we are green across the board for our Haste rocket, the payload, and the range here at NASA's Wallops Flight Facility. And today we'll be taking the DIU's next experimental hypersonic mission to the skies to deploy DART-AE, a scramjet-powered aircraft developed by Australian aerospace engineering firm Hypersonix, with an X, and with a nod to their payload and Australia's classic cultural icon, Crocodile Dundee. We are calling this launch That's Not a Knife.
Today's mission marks the historic first flight of DART-AE, which will be used to validate the aircraft's propulsion, materials, sensors, and guidance technology under real hypersonic flight conditions. At the heart of DART's 3D printed airframe is its scramjet engine, an air-breathing system similar to that of a jet engine. Now it uses oxygen in the atmosphere to combust with fuel, generating the thrust needed to fly at hypersonic speeds. This innovative design is part of Hypersonic's mission to create a low-cost, multi-mission hypersonic aircraft for applications in defence, aviation and aerospace. And now, here's more from Hypersonix about DART-AE.
The time is right for Hypersonix. The purpose of Hypersonix is to build and fly hypersonic aircraft. We are out in front in terms of our scramjet technology, so the propulsion, but also our vehicle designs.
We believe it's going to change the way we fly. It really is about that technology as much as the application of that technology.
The other great thing about the scramjet tech that we use, it's air breathing and it uses hydrogen as fuel, so we're not creating any pollution.
What we develop here will have wide-ranging applications across aerospace.
We have this long-term target of flying at Mach 12, and at the moment, Mach 12 for sustained flight, it's kind of in the realm of science fiction. So what we need to do is break down that path to flying at Mach 12 into discrete milestones. The first of those milestones, the first flight activity that Hypersonix is going to perform is DART at Mach 7.
When you travel hypersonic, the main issue is heating.
DART will be glowing red hot and 1,000 degrees, but we have to keep the sensitive electronics on the inside at under their maximum temperatures, and we don't have very much space to do that. DART is a demonstrator to fly at hypersonic speeds, but it's also to collect data and to learn so that we can keep pushing forward and make vehicles that travel up to Mach 12.
The thing about flying fast is you always end up with a really cool looking plane. We've developed this scramjet technology and hypersonic vehicle technology over the last 30 years. So it's come together, it's very mature. And then we have all these other opportunities of new materials, the commercial off-the-shelf hydrogen tech, and the computing power that we use in our analysis.
We've got the best partners on the planet to help us do that. We're dealing with partners such as Kratos, DIU, and Rocket Lab.
We also have a lot of smaller companies here in Brisbane, but also throughout Australia that help take our tech from the design to the real physical thing.
In order to fly at Mach 7, we need to overcome a whole bunch of engineering and materials and technology challenges, and what we're working on at the moment are tackling those challenges one by one.
We've got the team, we've got the technology, and we've got a way of being able to build what we build in a high cadence. And I think that's why organisations like the Defence Innovation Unit, that's exactly why they deal with people and companies like us, because we can move a lot faster.
The goal at Hypersonix is not just to enable hypersonic flight, but to commercialise it for everybody.
It's for the planet. I think we're building a platform using hypersonic technology, particularly scramjet, that are hydrogen powered, and we're looking to deploy that technology across various aerospace applications. We see the planet as the beneficiary of what we're doing in the longer term.
Launching DART-AE on Haste is a very exciting moment for the Hypersonix team and one that reflects years of engineering work to bring a reusable, sustainable and strategically relevant hypersonic technology online for the United States and its allies.
And they won't have to wait much longer to see DART-AE leave the launch pad for its first ever flight, now that we are just T-minus 17 minutes in the countdown to liftoff. At T-minus 16 minutes, our teams will enter into the go, no-go poll for today's launch from our Mission Control Center in Virginia. This is the final readiness check that takes place before liftoff, where the launch director will ask each team member for a clear go or no-go to proceed. One by one, responsible team members will confirm that their systems are working as they should and that there are no concerns leading up to the final count.
If everyone reports go, then Rocket Lab's launch director, Paula Terrace-Serralonga, will confirm that we will proceed through the final minutes and then on to liftoff. That poll is about to begin, so let's listen in now.
How did you scan down?
Jesse LD.
Umbilical and arm and prime sequence complete.
Thank you. And to all stations, LD on countdown proceeding with the final poll for launch, go, no-go sequence, starting with the stage.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC is go.
Vicon.
Vicon is go.
GC.
GC is go.
PLS.
PLS is go.
Mars CE.
Mars CE is go.
Mars Ops.
Mars Ops is go.
Was quite quiet Mars Ops, Mars 1.
Mars 1 is go.
And continue with NASA GSO.
GSO go.
NASA RSO.
RSO is go.
NASA PM.
Go.
LD SAP.
LD sub is go.
NASA TD.
Go.
Can you just repeat TD, please?
TD is go.
Understood, TD. We'll be standing by for final go for a mission director poll.
Beautiful. That was a clean series of goes across our team, pending the mission director's go as well. Otherwise, we are on track with today's launch attempt at 4:50 p.m. Eastern Time. Now, if anything changes, we have a couple of hours into the rest of the afternoon to reset that clock for another attempt.
Now, earlier in the count, we checked in with the team at Launch Complex 2 on Wallops Island as they conducted vehicle checkouts on Haste, ensuring everything was ready before the vehicle was raised vertical on the pad. Now, our range coordinator, David Stiles, is here to take us through what's involved in those early launch operations.
Good morning. On this glorious day here at Wallops Island, I'm David Stiles, the range coordinator for Rocket Lab here on the eastern shore of Virginia. And directly behind me is our Haste rocket on the pad at Launch Complex 2 within the Mid-Atlantic Regional Spaceport. The team behind me are getting ready to go for our latest hypersonic test launch for the DIU. It's a crisp 40 degrees out here at the pad, where our launch technicians run through a full day of launch operations before liftoff. Starting from about T-minus 9 hours, we work through general pad system setup before we connect Haste Stage 1 umbilical. That's the critical power line that connects the rocket to our ground support system all the way up until just before liftoff. At the same time, just a few miles down the road, our launch operators check in to their consoles in our Mission Control Center. Once those early checkouts are complete, the team takes Haste vertical just a couple of hours later and run an igniter test sequence of the Rutherford engines, making sure the propulsion system is fully primed and ready for the launch ahead. In the hours that follow, the team load the rocket with its kerosene propellant, as well as run checks across our ground stations and avionics before we get into the lock system chill and load sequence at around 3 hours before launch. The range safety status comes in around 60 minutes and T-minus 30 minutes before launch. And then we move into the go, no-go poll with the launch director at T-minus 16 minutes in the count. It's a full-on run of operations here at LC2 with a busy team both down at the pad and at their consoles. And keeping busy right next door to LC2 is our Neutron team working on Launch Complex 3. LC3 is our new launch, test, and landing site for our much bigger reusable rocket on the horizon. While we officially opened up that site last year, you might notice a new structure mounted to the top. That's the test tower for Neutron's second stage. Our engineers and technicians are also working through infrastructure and fluid systems commissioning, including cryo-shocking the 3 15,000-gallon liquid nitrogen tanks we have on site and the pair of 90,000-gallon liquid oxygen tanks that make up the tank farm. It's been really fantastic to watch it all come together while Electron and Haste launch operations carry on right next door. It's a beautiful day to launch another rocket from LC2. I know everyone here is super excited to watch another Haste mission fly. Go Haste and go Rocket Lab.
And here we are now, T-minus 10 minutes or so on the clock, almost ready for launch with our second flight from Wallops Island for the DIU in just a matter of months.
As we count down to the launch of That's Not a Knife, here's more about our Haste rocket flying today's mission. Haste is an acronym that stands for Hypersonic Accelerator Suborbital Test Electron. And while it does look a lot like our usual Electron rocket, there are a few key differences that make it the perfect platform for experimental hypersonic test flights, just like today's mission. For a standard orbital launch, Electron achieves orbital velocity to deploy payloads above the Kármán line, which is over 100 kilometers above Earth, before continuing onward to orbit. Our suborbital rocket Haste, on the other hand, operates in a similar way but achieves slightly lower velocities and altitudes to allow us to test technologies at hypersonic speeds closer to the ground.
Now, hypersonic velocities are anything above Mach 5, or 5 times the speed of sound, compared to, for example, a commercial airliner that flies subsonic, which is slower than the speed of sound. Then you've got supersonic, which is the range above subsonic all the way up to Mach 5. Now, above Mach 5, those are speeds faster than the fastest fighter jet you know about. And then there is our Haste vehicle, which flies well beyond that and is capable of velocities all the way up to Mach 20.
Now that opens up a range of test capabilities for mission partners like the DIU and Hypersonix, where thermal properties, tracking and control can be tested in real hypersonic flight environments, which can't be replicated on the ground. And that's exactly what today's experiment is all about. After it launches off the pad, our Haste rocket will boost DART-AE to hypersonic speeds before it's released horizontally to free fly on its own under aerodynamic control and scramjet propulsion.
Now, Haste's out-of-the-box hypersonic capability is being well leveraged for higher cadence and more affordable hypersonic test flights. And today's launch is our 4th hypersonic test mission in under 6 months from LC2, which is exactly addressing the needs of what the US government is looking for, with more frequent and reliable flight opportunities to develop hypersonic capabilities. So here's more about Haste.
The world is accelerating, and so are the threats we face. Escalating geopolitical tension has revealed a critical defense capability gap, a challenge defined by Mach 5 and beyond, the speed of hypersonics.
The threat is very real. Time is of the essence. If the adversaries, if the great power competition states are developing this type of capability, we need to have defensive capability to protect the U.S. and our assets overseas. Golden Dome at its essence is a missile defense technology. It is to protect the U.S. homeland from threats. You don't want the first time you try that out to be live fire when everything is on the line.
For decades, America's approach to testing these critical capabilities was plagued by high costs and slow cadence. The status quo was simply too slow for the scale of the threat.
Historically, the programs have been many years in development, so think thousands and thousands of engineering hours over a 2-year refurbishment cycle for these old Peacekeeper missiles, a new launch campaign, and a new payload development, plus all the downrange assets, hundreds of millions of dollars, and you get one launch.
The mandate was clear: lower the cost barrier and dramatically increase the launch tempo. To answer this challenge, Rocket Lab engineered the Hypersonic Accelerator Suborbital Test Electron, also known as Haste.
Haste is a converted Electron into a suborbital platform for testing research payloads at hypersonic velocities. The heritage systems have all been solid-fueled bottle rockets. You light them and they go. Here, we can throttle, we can gimbal, we can get into Mach 20s with this platform, and all the way down to Mach 7.
Based on the flight-proven, liquid-fueled Electron, Haste is fundamentally different. It gives testers unprecedented control over flight profiles and environments.
We can also do very interesting things like offload propellant, vary the exit velocity so we can go faster or slower. We can target downrange positions for payload release.
This unique platform immediately shattered the industry paradigm, moving testing from a single launch per year to the speed of commercial production.
The predominant bottleneck is launch availability. We've shown that you're going from one launch a year, hundreds of millions of dollars, to multiple launches a week. We did 2 Haste launches in basically a week and a half. That could have been years between testing, but instead it was back-to-back.
Leveraging the flight heritage of Electron, Haste offers a reliability and repeatability unmatched by any system in the world.
So Electron is launched over 70 times now. It's very well understood. It's very high-performing. A commercial speed and scale and price point, I don't think anything's ever existed like it.
Hypersonic defense systems cannot be left to chance. The ultimate goal of Haste is to provide the data needed to secure the reliability of the nation's protective shield.
Space-based interceptors is a completely unproven technology, but it's critical to the Golden Dome architecture. So the ability to test these defensive systems is crucial. It has to be affordable and it has to be high cadence. So that's what Haste provides. We can go fast, we can go affordably, the full soup to nuts capability. So that's production, that's logistics, it's a well-seasoned launch team. It's launch infrastructure like a launch range, but you got to be able to put it all together. You can't name another flight test platform that is launching as repeatably, as reliably, or affordably as Haste is, and that's what's really changing the game in terms of getting more data sooner. Me and many other people working the Haste program are very proud to be working on something that leads to deterrence and in a bad day will protect the lives of American citizens.
At T-minus 5 minutes on the clock, we're coming up now to the final few moments on the pad for That's Not a Knife. But before we get to the launch auto sequence, today's flight profile is going to be a little bit different to the orbital Electron missions that you're probably used to watching. While those launches usually reach their target orbital velocities and altitudes after 9 minutes of flight, Haste's mission will be complete within less than a third of that. Now, at the request of the customer, you won't see the staging events between the vehicle's first and second stages, or the shutdown of the 9 Rutherford engines at main engine cutoff.
In fact, soon after main engine cutoff is when Haste's mission will end. Within fractions of a second after MECO, Haste's fairing will separate and Dart AE will be deployed. And we won't hear it across the nets from Mission Control either, but we will stay live on air through those mission milestones to call out when those actions are expected to happen in real time. And all in all, we are expecting just over 2.5 minutes of flight time to boost Haste to hypersonic speed, and then it is over to Dart to carry out its mission objectives for Hypersonix and the DIU.
It's going to be fast and exciting to experience in real time. But first, we have to enter the launch's countdown auto sequence, which starts at T-minus 2 minutes to liftoff. At that point, the Haste rocket will switch to internal power and take over control of the countdown. At the same time, its launch safety system will be enabled and Mission Control will call out both of these actions across the nets. A few moments later, the rocket's liquid oxygen propellant loading should be complete, and that's another milestone we can expect to hear from Mission Control.
At under 1 minute to lift off, the propellant tanks will be at their optimum pressure levels for launch. Ground control will then confirm that the water deluge system on the pad is ready to be activated for when those engines on the rocket ignite. Then we get a 30-second notice to launch before the launch director counts down with the clock from T-minus 10 seconds. The engines will ignite at T-minus 3 seconds, and the launch pad's hold-down mechanisms will be released for Haste to take flight at T0. Okay, taking a look at the clock on the top left-hand screen there, we've got a pause in that countdown. So we're going to bring up the audio channels from Mission Control and have a listen.
LD avionics.
Avionics, proceed with avionics terminal abort checks, sequence 73.
Copy sequence 73 and work.
And stage LD on countdown.
LD stage.
Stage, proceed with the stage terminal abort checks, sequence 74.
Copy Mach.
And 12 station LD on countdown. While the operators are working on their terminal abort checks, we'll be working on the recycle sequence.
Vehicles on external power.
We've entered a hold at T-3 minutes for upper level winds, which we knew was a possibility for today's mission. So let's listen in to see if the clock can be reset soon.
Not tracking.
Now, the teams are working through checks to determine a new T0 based on evolving weather data. While we wait, we thought we'd take a look back at all 21 of last year's liftoffs in what was a record year for us. Join us with a quick walk down memory lane.
3, 2, 1.
That was 2025, a massive year for the team, and we are looking forward to making this year even bigger. And today's launch will be our third mission for 2026, with many more booked after this. But back to today, the wind is tracking down, which is exactly what we want to hear, but we're still waiting for that new T0. So let's keep the nets up so we can hear that call out from the launch director.
T minus 60 minutes hold, so same as we would be holding at our nominal T. Mars Ops.
Mars Ops is go.
Mars 1.
Mars 1 is go.
NASA GSO.
Go.
NASA RSO.
Those go.
NASA PM.
Go.
LDSAP.
LD-SUP is go.
NASA TD.
Go.
Copy, all standing by for the go for the mission director poll.
You heard it there. We have the go from the launch team to proceed with today's liftoff, pending confirmation from the mission director. Right now, we are at T minus 14 minutes to launch, and we are looking green across the board.
LDMM on countdown, ready to resume polling.
Copy, on behalf customer.
Go, MD go.
Copy. The go no-go sequence is complete. We are T minus 11 minutes, 10 seconds and counting. This time we're go for terminal count starting at T minus 10 minutes.
Great to have that go from the mission director. And as the clock continues to count down to liftoff, why don't we take a look at the rocket on the pad for today's mission? Now, aside from the difference in mission purposes, there is a lot about Haste that you'll likely recognize from our orbital Electron rocket with a few key differences. This one is standing at 20 meters on the pad, and so Haste is a couple of meters taller compared to a standard Electron, with a longer fairing that accommodates the DART aircraft that is on board. Also, since Haste flies at lower altitudes, it runs a larger payload capacity of up to 700 kilograms, and its kick stage is tailored to the mission's precise conditions and tip-off requirements. Otherwise, from the stage 2 down, Haste leverages much of the same technology that has powered our 80-plus Electron launches to date, and that includes the same carbon composite material used throughout its structures that keeps it lightweight and durable at both hypersonic and orbital velocities.
That's right, and Haste also uses the same engine configuration as Electron, with 9 3D printed Rutherford engines at the bottom of the first stage that powers its flight. Now, the beauty of our liquid-fueled engines is their ability to gimbal and throttle, which opens up a variety of trajectories that our customers can test their technology with, much like today's mission.
Avionics LD on countdown.
LD avionics.
Avionics proceed with sequence 61 avionics terminal checks.
Copy and work. S-band to switch to high power for flight.
Stage LD on countdown.
LD stage.
Stage proceed with the sequence 62 stage terminal checks.
Copy and work.
High voltage batteries are ready for flight.
GCLD on countdown.
How did you see?
GC proceed with sequence 63 launchpad ready.
Understood to work.
All pump lips nominal, all engines ready. LD stage countdown.
Stage LD.
That's the stage terminal checks complete.
Copy.
LD avionics on countdown.
Avionics LD.
Avionics terminal checks complete.
Copy avionics.
Strong bar projected for flight. Hold down mechanisms armed.
We are now at T minus 4.5 minutes, and shortly we will have to enter the launch's countdown auto sequence, which starts at T minus 2 minutes to liftoff. That's when the rocket will switch to internal power and take over control autonomously. A few moments later, the rocket's LOX propellant loading should be complete and in recirculation.
Then again, at under 1 minute to liftoff, the propellant tanks will be fully pressurized for launch, and our ground controller will confirm that the water deluge system on the pad is ready to be activated for when those engines ignite. Then it is 30 seconds until launch before the LD starts to count down with the clock from T minus 10 seconds. It's full noise at T minus 3 seconds when those engines ignite, and then the launch pad's hold down mechanisms release for Haste to take flight at T0.
We're going to bring up the audio channels now for Mission Control to listen along to those milestones in real time. We'll be back with you shortly after liftoff for those 2.5 minutes of hypersonic flight for That's Not a Knife. Go Haste, go DIU, and go Hypersonics.
And all stations, we are T minus 3 minutes and counting. At this time, the 3-warp procedure is in effect. From now on, there should be no red flags on your critical LCCs. VCON LD on countdown.
LD VCON.
The count has been held.
Yeah.
Hold.
That is a hold on the countdown clock. We are paused at T minus 2 minutes 56 seconds to lift off. So let's wait to hear for an update from Mission Control.
Confirmed.
GCLD on countdown.
LDGC.
GC confirm the stage 1 and stage 2 umbilical status are engaged.
Confirm engaged.
Copy and please proceed with the secure LB on path and enable ECS.
Understood work.
Thank you. Avionics LD on countdown.
LD avionics.
Avionics proceed with avionics terminal board checks sequence 73.
Copy and work.
Stage LD on countdown.
LD stage.
Stage proceed with stage terminal board checks sequence 74.
Copy and back.
Vehicles on external power.
LD stage mission.
LD stage countdown.
Stage LD.
That's the stage terminal abort checks complete.
Copy, thank you.
LD avionics on countdown.
Avionics LD.
Avionics terminal abort checks complete.
Copy, thank you.
Okay, once again, that clock at the top left-hand corner of the screen has restarted, counting down to the final opportunity in today's launch window. We are, however, still waiting to hear the confirmed new T0 time from the launch director, so we're keeping up the audio channels from Mission Control, waiting to hear that call from her hopefully soon.
GC on countdown.
GCLD.
We secured on the pad, ECS is enabled.
Copy. Control station LD on countdown. You may have seen targeting the end of the window. That's 00, column 00, column 00 UTC time, now on the 28th of February. And all operators continue monitoring your critical systems and be prepared for the go, no go, and starting the count at T-minus 60 minutes as usual. And I confirm that I'm actively monitoring countdown cord, LV cord, range cord, and safety net.
Okay, just backing up what we heard from our launch director there for the new T0 time for today's launch attempt. We are now targeting 7 p.m. local time Eastern, which is 0000 UTC for today's opportunity.
LD Vicon countdown.
Vicon LD.
12,200 is complete.
Thank you, Vicon.
All right, we are at T minus 16 minutes and 30 seconds, heading towards the final go, no-go poll for the last opportunity today. We are currently looking green across the board, pending confirmation from the mission director that the customer is go, then we'll be proceeding through to T0. Over to mission control now.
To all stations, LD on countdown, proceeding with the final poll for launch. Go, no, go sequence, starting with the stage.
Stages go.
Avionic.
Avionics is go.
GNC.
GNC is go.
Vicon.
Vicon is go.
GC.
GC is go.
PLS.
PLS is go.
Mars CE.
Mars CE is go.
Mars Ops.
Mars Ops is go.
Mars One.
Mars 1 is go.
NASA GSO.
Go.
NASA RSO.
Those go.
NASA PM.
Go.
LD SUP.
LD SUP is go.
NASA TD.
Go.
Copy, all standing by for go for the mission director poll.
Excellent news out of Mission Control. The local and support teams are go for launch and we are proceeding through the count. A reminder that today's T0 is now set for 7 p.m. Eastern Time or 0000 UTC. We've got about 14 and a half minutes remaining in the count.
LD on countdown, ready to proceed with the go, no go poll.
Copy, MM.
All right, go, MD, go for terminal count.
Copy, the go, no go sequence is now complete. We are T minus 11 minutes, 18 seconds and counting. This time we are go for terminal count starting at T minus 10 minutes.
That's the last confirmation we needed from the mission director and mission management. We are go to proceed towards liftoff. All right, well, while we have a little bit more time to wait, we did hear earlier in the show from our range coordinator, David Stiles, about busy operations at Launch Complex 3, right next door, for our new medium lift rocket Neutron. And last month, hardware began flowing to the launch site, starting with the reusable Hungry Hippo fairing. So let's check it out. So there it is, right down the road. We are thrilled to see hardware arriving to that assembly and integration complex just out there on Wallops Island.
High voltage batteries are ready for flight.
Stage LD on countdown.
LD stage.
Stage proceed with sequence 62, stage terminal checks.
Copy, Mach.
GC LD on countdown.
LDGC.
Proceed with sequence 63, launch pad ready.
Understood, launch pad ready to work.
All pump lips nominal, all engines ready. LD stage countdown.
Stage LD.
That's the stage terminal checks complete.
Copy stage.
LD avionics on countdown.
Avionics LD.
Avionics terminal checks complete.
Copy, thank you.
Combat retracted for flight. Hold dead mechanisms armed.
T minus 4 minutes and 50 seconds, and shortly we are nearing terminal count, scheduled to start at T minus 2 minutes. That will kick off a series of events for Haste, making sure its fuel and oxidizer tanks are pressurized and ready for launch, and activating the final ground system, the Deluge. The Deluge is dual purpose. It obviously keeps things nice and cool, but is also imperative for sound suppression, keeping our 9 Rutherford engines considerably quieter.
That's right. And then we will hear a 30-second call out followed by the final 10-second countdown from the launch director and mission control ahead of engine start at T-minus 3 seconds. So let's throw it back to the team in mission control for the final moments ahead of liftoff, and we will be back with you once we are in flight.
ECS disabled, pilot auto sequence is armed, pilot is ready for launch.
Thank you, Jesse. Control stations, we are T-minus 3 minutes and counting. At this time, the 3-core procedure is in effect. From now on, there should be no red flags in your critical LCCs. VCON, LD on countdown.
LD VCON.
VCON, log the auto sequence and confirm.
Locked.
And confirm VCON, all flight computer ASGOs are green.
All ASGOs are green.
Thank you, VCON. We're go for auto sequence start T-minus 2 minutes. At this time, LDs go for launch.
The vehicle is fully on internal power. RF reception is nominal, and AFTS is green and enabled for flight. Lock load is complete. System is in recirculation. Anti-geysering is disabled.
Stage 1 tank suppressed.
High flow engine port enabled.
T-minus 20 seconds and counting.
Stage 2 tank suppressed.
Stage activated.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. Liftoff.
Vehicle is flipped past, vehicle past. Beginning pitch over.
Stage 1 propulsion is nominal.
Well, that's not a knife. That is our Haste rocket on your screen there with a textbook launch off the pad at LC2 on Wallops Island. Haste is climbing fast now at almost 900 kilometers an hour with an almost immediate pitch over to follow today's suborbital trajectory. Max Q, or maximum aerodynamic pressure, is up next. So standing by now with mission control.
Approaching max Q. Cleared max Q.
A nice clean sail through Max Q by Haste there, now at speeds of more than 2,000 kilometers an hour. Hearing good calls from mission control as well. High voltage battery discharge should be happening as we need it to for those 9 stage 1 Rutherford engines at the bottom of the rocket. And coming up soon will be MECO, or main engine cutoff of those engines, which is when all 9 of them power down at the same time. And now usually that is to allow for the first stage to separate from the second, but with this experimental hypersonic mission, we are doing things differently. And so, at about the same time as those engines shut down, Haste's fairing will separate and DART will be deployed to begin its free flight at hypersonic speed.
A reminder that at our customer's request, we'll be cutting the camera view just before MECO, fairing separation and payload deployment, but we will mark the moments we're expecting those actions to take place before DART AE flies the rest of the mission. So let's watch and listen now.
Stand by for MECO.
Okay, and with the clock now past 2 minutes and 45 seconds into flight, that marks our expected main engine cutoff, fairing jettison from Haste, and deployment of Hypersonix DART AE aircraft at hypersonic speed to continue on with their mission.
Right now, the team will be testing the aircraft's aerodynamic control at several times the speed of sound, as well as its scramjet propulsion to power the vehicle along its suborbital trajectory. Good luck to the DIU and Hypersonix for the remainder of the mission.
So Haste's role in this launch is otherwise complete. Another hypersonic test launch with 100% mission success out of Launch Complex 2 on Wallops Island. And this is our second hypersonic flight for the DIU in just 3 months, and our 7th Haste launch overall to test technology in those real-life conditions. This mission is also our 11th overall launch from Launch Complex 2 on Wallops Island within both the Mid-Atlantic Regional Spaceport and NASA's Wallops Flight Facility. So, congratulations and thank you to our launch partners for your ongoing support.
And since we're rounding out with numbers, today's launch is our 82nd launch in total and 3rd launch this year, with our next mission scheduled to take place in just a few days' time. But this time from Launch Complex 1 on the opposite side of the world. Make sure you check out our social pages and website for more info. Otherwise, thank you so much for joining us for this mission today. We'll see you back here soon. This is Rocket Lab Mission Control, signing off.